Have you ever wondered what would happen if you converted an Excel spreadsheet to an audio file, or an MP4 video to a PDF document? Or maybe there's some other exotic combination worth trying out, but I guess we'll never know, because most online file converters only let you select formats in the same medium: images to images, videos to videos, text documents to fancier text documents, and so on. What if there was a service that could natively convert a Portal 2 demo file to a Flash animation, for example, and did so completely locally? All of these online tools upload your files to a server which does all the processing. I'm sure you can imagine why that's terrible for privacy. In fact, I cannot stress this enough. Uploading personal files to a random internet server is one of the most careless things that we've normalized. So I'm imagining a website that can convert anything to anything and locally in your own browser. These are the main two goals that I set out with to build my own file converter. If you don't care about how I did it, here's the link. You can go and try it for yourself. Though, bit of a heads up, there is a reason why no one has done this before, and that's what I'll be talking about in this video. Specifically, the elephant in the room is no doubt the promise of converting between two completely different mediums. Like, what would it even mean to convert an MP4 video to a PDF? Well, as you might already know, videos consist of multiple sequential frames, and a PDF document consists of multiple sequential pages. When you frame it like that, the process becomes pretty clear. You extract the video's frames into a series of images, and then build a PDF file with pages containing those images. But here, I want you to notice that we're actually dealing with two problems at once. Sure, we have to convert between file formats like MP4, PNG, and PDF, but we also have to convert between different forms of media, like digital images to document pages. For videos and documents, this is pretty straightforward, but things do get a bit more complicated when you're converting images to audio, for example. Even though you might support the JPEG format and the MP3 format, that doesn't make it any easier to figure out how an image becomes sound. Let's start with the easier problem for now, which is that we need to support as many file formats as possible. Now remember, this is supposed to be a website that does all of the computation on the client's computer. That makes things a bit more challenging than usual, because it means we can't just spin up VLC to decode a video, for example. The tools we use have to be compatible with a web browser. Take audiovisual media as an example. The most popular utilities for such formats are FFmpeg for video and audio, and ImageMagick for images. If you've never heard of them, you might be surprised to find that they're the backbone of many media-focused services. Even YouTube uses FFmpeg for transcoding video. At least sometimes. Nowadays, they do of course have proprietary tech to do the more common stuff. While ImageMagick and FFmpeg are usually native computer programs meant to run on a desktop PC or a server, people have ported them to WebAssembly, a technology that makes it possible to run them in a browser. This alone is a great starting point. Just these two would already make for a competent file converter for images and videos, even supporting some truly exotic formats. FFmpeg can even read BINC, which is the video format used in most Valve games. But I, of course, have no plans of stopping here. Let's also not forget that the average browser already has some built-in media capabilities. I mean, how else would it decode the video you're watching? Of course, in the majority of cases, our specialized tools do a much better job, but still, the built-in stuff can be useful sometimes. For example, the WebAssembly port of ImageMagick doesn't come with support for WebP images. However, most browsers can handle WebP. So I wrote a little script that renders the WebP on an invisible canvas, and then effectively screenshots that to turn it into a PNG. That PNG can then be fed directly into ImageMagick. So I've basically added support for an extra format with no additional cost. Another thing that browsers are good at is rendering documents. I mean, think about it. Why would I include a separate tool for parsing web pages or vector graphics if that's literally what your browser does all the time? I can take the contents of an HTML document, embed it in an SVG image using the foreign object tag, and then, just like before, put it on an invisible canvas and screenshot it into an image. But of course, when I say document, you probably aren't thinking of a web page. you are probably thinking of Office documents, like those of Microsoft Word, PowerPoint, Excel, and so on. Unfortunately, there doesn't seem to be an all-in-one solution for parsing these on a browser. Sure, there are one-off tools specialized in handling one format at a time, and there are projects that glue them together, but that quickly becomes a bloated mess. On its own, this could have been brushed aside as an inconvenience, but that's still just the beginning. While there are options for all the major Microsoft document formats, there aren't as many for the open document alternatives. And concerning the tools that do exist, the most popular Word document to HTML parser Mammoth converts a document like this to this. It's not hard to spot the difference. And sure, I could patch it to add support for formatting, but Mammoth was never designed to do that. Its purpose is just to translate the document structure, and I'd be fighting the tool if I wanted authentic output. The only other reasonable alternative seemed to be including yet another commonly used open source media parser as a WebAssembly program. However, that would likely mean bundling LibreOffice, and as far as I can tell, this one's not as mature as the rest. It probably would give accurate results, but I was more worried about the size and loading times. So naturally, when the tools you want don't seem to exist, you go ahead and make your own. Yeah, I took a little bit of a detour to work on a standalone Office to HTML parser in pure JavaScript. In retrospect, this was probably a bad use of my time. There are 3 major steps to this: extracting the zip, parsing the XML, and rendering the document itself. The first one is exactly what it sounds like. A modern Microsoft Office or open document file is just a renamed zip file. Extracting zip files is a fairly common task, so I didn't really feel like reinventing the wheel on this one. That said, the existing libraries come with a bunch of stuff that I do not need, like support for creating zip files, which I never plan to do, and support for decompression algorithms, which I will never use. So instead, I got Claude to implement the bare minimum so that I could focus more on the important aspects like parsing XML. XML stands for Extensible Markup Language, and it's basically a somewhat human-readable data structure used for all sorts of things. When you extract a Word document, these are the files you'll find hidden within. They are what describe the document's entire layout and formatting. Now, if you've ever seen HTML, you might notice that XML looks very similar. Most browsers actually do support parsing XML data, but I wanted to make sure that this code can be used outside of a browser too. Luckily, writing an XML parser is not at all difficult to do. My implementation came in at about 70 lines of code, and while it probably won't work for everything, it serves its purpose in my specific use case. Now all that's left is to parse the actual document. I will say, the open document stuff is so much nicer to work with than Microsoft's format. It often translates directly to HTML with very little need for additional logic, and the components are directly reusable. You can pretty much just throw a presentation into the text document parser and it'll almost kinda work. Open document files also come with a thumbnail image, so if my parser ever crashes on something, it can at least still render a blurry copy of the first page. Anyway, here are the results of my parser compared to the source document. And here they are compared to Mammoth's output. To be clear, I'm not throwing shade at Mammoth, it's just not the right tool here. Of course, my tool also supports parsing PowerPoint and Excel documents to a limited extent. In retrospect, I'm sure that forking and skimming LibreOffice would have been the correct approach, and my makeshift custom tool likely doesn't have the stability of all the others, but hey, at least it supports formatting. I'm definitely way past recovery from the sunk cost fallacy at this point, so I kind of have to use this, even if I think LibreOffice would be a better fit. As you can probably tell by now, this is not a serious project. This is just me goofing around with a silly idea, hoping to make something mildly practical out of it. That said, if you do genuinely want to improve either of these tools, the GitHub links are in the description. And also in the description is a link to this video's sponsor, Kodi.tech. I've talked a lot about Kodi on this channel and their hands-on approach to learning programming languages. Many people have pointed out that it feels kind of like Duolingo, but for programming. But one thing that I haven't mentioned yet is their courses. These are sets of practical lessons and challenges which walk you through the process of building real programs. Frankly, I wish I had discovered this feature sooner, because I think it solves a fundamental problem that many learners have, which is that they often don't know what to make. Kodi's courses focus on specific goals and teach you everything you need to know so that, by the end of it, you will have built your very own solution to a real programming task. The courses are maintained by real people and the Kodi team, though if you ever get stuck, they do of course have an AI assistant built into the editor. That said, if you'd rather take it easy and learn the fundamentals of your language step by step, their coding journeys are still a great way to learn the relevant programming languages of today. So, if any of that caught your attention, check them out by using the link in the description. Let's take a break from the file format stuff for a moment to talk about the second major problem: converting between mediums. For visual stuff like images, videos, documents, animations, fonts, and so on, the answer seems to be pretty obvious. Just convert them to an image. Sure, you might lose some quality and details along the way, particularly when dealing with vector graphics, but the result will likely be more or less what you expect. Raster images are a good enough common factor for lots of different files. But what about audio? Sound doesn't convert to an image in any obvious way. Some audio files may embed album art, which you could extract, but that's not really what we're talking about, is it? We need to find a way to represent sound visually. Right away, you might propose a couple of naive ways of going about this. For example, you could dump the audio data straight into the pixel data, but that would just leave you with a bunch of incoherent noise. You might also think to simply draw the audio waveform, but that wouldn't explain how images convert back to audio. A waveform is one-dimensional. At any point along the x-axis, there's only one corresponding point on the y-axis. This is simply not true for an arbitrary image. How are you gonna get a wave from this? No, I want a solution that creates a semantically significant image from the input audio, and can also produce a semantically significant audio file from any input image. The solutions we've discussed so far dabble in the spatial domain, but for this, we'll have to dive into the frequency domain. You might remember from physics class that all sound is just a wave. Any regular wave can be described using just a few parameters: the frequency, which is how close the peaks are from each other horizontally, the amplitude, which is the distance between the highest and lowest point, and the phase, which is the offset from the start of the wave. Basically, you can think of these as different ways to squish, stretch, and move the wave around. Audio engineers are likely boiling in rage right now due to the oversimplification, but this explanation will do for now. However, a regular wave will only produce one constant tone. More complicated sounds have to layer multiple waves on top of each other and change them over time to produce a waveform. That's ultimately all that an audio file is. It's just the final wave gained by summing all of its component waves. So, to get an additional dimension for our image, we can split this waveform back into its component waves by using what's called a discrete Fourier transform. This way, each point on the x-axis now corresponds to multiple points on the y-axis, just like pixels in an image. To actually translate this to pixels, we can order the waves by frequency along the y-axis. Then, for each fragment of the wave, the red and green color channels encode that wave's amplitude, while the blue color channel encodes the phase. And just like that, we've represented a waveform as a raster image. Not only that, we can then reverse this whole process to get back the input audio file. Or, because this is just a grid of pixels, we can even convert arbitrary images to audio, though that probably won't sound very good. Of course, I'm massively oversimplifying this whole process. I'm not at all an expert on audio processing, so my implementation introduces quite a bit of noise in certain areas. If you think you can help improve this, please do. Again, the GitHub link is in the description. With audio and visual media covered, you might be tempted to say that that's it. Computers only display pictures and play sound, so surely that's all you need to represent all digital media. But let's look at this from a different perspective. Audio, as we've already discussed, is one-dimensional. Images are two-dimensional, so that of course raises the question: do we have any three-dimensional media? The most obvious answer comes in the form of 3D models. I mean, think about it. This raises the exact same problems that audio did. Representing a 3D model as a 2D render loses a whole dimension of information. For that same reason, it's also not a reversible process. My immediate reaction would be to slice the model on every vertex along some axis. You could then use a library like Three.js to render the slices with an isometric camera and a depth-based shader. This would allow you to later reconstruct the model from the slices based on their shape and pixel brightness. At least that's the idea. This is definitely outside of my area of expertise, and this project is already dragging on longer than it should. If you're up for the task, community contributions are once again welcome here. Thankfully, I don't think I can come up with any examples of four-dimensional media, so... well, actually, no. 3D animations do count as four-dimensional. I suppose you could divide them into multiple output files like we already do for videos, but... again, I'll just stick with 2 dimensions for now. So, all that's left is to figure out how exactly all of these tools link together. Let's say you have a tool that handles videos and a tool that handles images. You've been tasked to convert an MP4 video into a series of PNGs. Neither of these tools can do that on its own, so you'll have to find a way to link them together. To do that, you can look at the list of formats supported by both tools and find one that they have in common. In this case, both FFmpeg and ImageMagick natively support the GIF format. It's not quite an image, but it's also not quite a video. So, your MP4 can become a GIF, and that GIF can then become PNG. By this logic, we can algorithmically determine whether any one tool is compatible with another. You just need a list of formats outputted by the first tool and a list of formats accepted by the second tool. If there's a match in these lists, you've got a connection. So then, the big idea is to throw all of our tools into one big pile and have the program route through all of them to get from point A to point B, chaining different formats along the way. It's also important to note that we don't just want any path. We want the shortest path with the fewest links to improve speed and reduce quality loss. We also want to weigh our choices towards more mainstream and ideally lossless formats for that same reason. I think it helps to visualize the different tools as nodes in a tree-like data structure. We start at a root node and make a list of all the tools compatible with our input. Then, we search each of these tools to see if they're capable of outputting our target format. Or, in other words, we're checking if they're connected to some target node. If they're not, we descend downwards and repeat the first step to generate a new list of child nodes. We again check if any of these tools are capable of outputting our target format, and if not, we move to an adjacent node, repeating the same process. This is a common tree search algorithm known as breadth-first search. It guarantees that whatever solution we find is the shortest one in terms of number of nodes, as we only descend downward when we've exhausted all options available on the current level. In order to bias the search towards more favorable formats, we can simply reorder the nodes horizontally so that the better formats are looked at first. And really, that's all there is to it. There's a bit more logic to make sure that we don't route through the same format more than once, and each candidate path is tested for errors, as some routes tend to only be compatible on paper and not in practice. But this also means that to add a new format, you just have to be able to convert it to and from just one of the already supported formats. The algorithm will then automatically find its way to everything else. Still, the algorithm itself is really not the hard part. The hard part is getting the required information out of all of these tools and standardizing it so that it can be cross-compared. Most file converter programs don't really keep a list of supported formats. It's surprisingly difficult to accurately label a file format. Take MP4 for example. It might seem like the .mp4 file extension would be a good enough label, but no, far from it. MP4 is really just a container for a range of video and audio formats. It might not matter much for the end user, but it does matter for the program doing the conversion. Is this an H.264 codec, H.265, AV1? Is the audio AAC or maybe Opus? This is actually the reason why some MP4 files embed in Discord while others don't. So, of course, FFmpeg lists MP4 in a group of a whole bunch of other containers. PNG has a similar issue. Yes, most of the time, the .png extension is sufficient, but not always. Animated PNGs are rare, but they do exist, and they often use the same .png extension. Getting this wrong could mean treating a video file as an image file, which is obviously not what we want. Other files have the opposite problem. Take XML for example. As previously discussed, this is used internally in Office documents, but it's also the backbone of SVG images and RSS feeds. These are obviously different mediums, but they all share the same underlying format. In order to better categorize each file in my system, I label them all by their MIME type. MIME stands for Multi-Purpose Internet Mail Extensions, and as the name suggests, this was initially a standard for email. But because of its usefulness in categorizing file formats by their semantic meaning, it's become a sort of de facto standard for all kinds of file-related things. Now, admittedly, this is still not a perfect system, but it is far better than just using file extensions. Still, there are many formats that simply don't have a MIME type, and plenty of other formats have too many MIME types. And in rare cases, one MIME type can correspond to multiple formats, as is the case with MP2 and MP3. Regardless of which way you look at it, there just is no universal way to identify a file. We're working with what we've got. Finally, let's talk performance. A website like this is obviously going to be very heavy. After all, we're making the user download tens of megabytes of binaries before they can even do anything. But if you're just here to convert a PNG to a JPEG and don't really care about all that exotic stuff, you probably don't need to load the video or document tools. You don't even need to load ImageMagick, really. Instead, we can simply cache the lists of supported formats and only load the actual programs when they're being used. Now, as you can imagine, the silliness of this project is defined solely by the formats that it supports. Sure, you can transcode your videos to MP4 or convert your images to PNG, but that's not as fun as a 20-page PDF document of the Valve intro. Also, that example from the start of the video wasn't a joke. This thing really does support rendering Portal 2 replay files. I know that absolutely nobody will ever use that feature, but I had to mention it here, so that the time spent adding it feels less like a waste. In an ideal world, this would support every file format to some degree. But of course, that's an unrealistically time-consuming task. That's why, once again, I invite you to contribute, if you can. All it takes to add support for a new format is to write a bit of code that converts it to something that we already support. From there, the algorithm can take it away and route you to literally any other format on the list automatically. So, as I said before, the links to this project, as well as the GitHub repositories, are in the description. Thanks for watching.